And thank you everyone for being here today. And like Bryan said, I'm going to tell you about what I've been working on in the lab. So I've been working on probe for GPR97. GPR97 is an adhesion GPCR that's found in many different tissues, especially the immune system and the bone marrow. It's thought to have an indispensable role in vertebrate bone formation. And it's cropping up in lots of different diseases here and there, but not really one defining one yet. Maybe when there's more structures, more small molecules to study, we'll find some more things. So one of the things that I like about IDG is that it allows you to end up in parts of the proteome that you maybe wouldn't have otherwise. And for me, this means studying adhesion GPCRs, many of which are orphans. There's 33 adhesion GPCRs. They are distinguished from typical GPCRs by being very large, especially having these large N-terminal domains that are often made up of many different components, as outlined at the bottom of this figure. I'm not going to go through all of this, but this just lets you see what makes adhesion GPCRs stand out. It also kind of lets you know that part of the way that these receptors are thought to be activated is by activation through these N-terminal domains, which could even include interactions with other receptors or another cell or pressure and things like that. So in this little corner right here is GPR97, and you can see my mock-up over here. There's not that many specific groups on the N-terminal region of GPR97, but it does still have this large N-terminal domain. It's thought that these N-terminal domains can be used to tune the activity of the receptor, possibly by laying down into the receptor and activating it that way, or deactivating, moving away, and tuning that way. There is this gain domain, this GPCR autoproteolysis inducing domain, which can self-cleave. So then you have this N-terminal region detached, and then it has the option of, again, interacting with the receptor or leaving, and you can possibly tune the receptor that way. It's thought that this N-terminal region probably sticks around with GPR97 because there's some cysteines that are formed between that region and the receptor. And then furthermore, once this N-terminal region is cleaved, there's this little guy in orange that's left known as the stachel sequence, which can act as a tethered peptide agonist. So again, this structure could interact with the receptor or not interact with the receptor and potentially tune it that way. So given that you've got all of these possible ways to activate adhesion GPCRs, they display a vastly unexploited pharmacological potential, especially in the fact that until 2012, there were no known small molecules that could activate any members of the GPCR, of the adhesion GPCR family. So in 2012, beclomethasone dipropionate was found to activate GPR97. It's a very exciting finding, but from a probe standpoint, starting with a very potent steroid is not really a great starting point. In addition to like steroid activity not being an off-target liability that you want to deal with, there's a lot of chiral centers here, and that's also not really something that you want to have to deal with. So in our lab, Wes and Tao, as part of general screening of libraries, screened over 8,000 compounds at GPR97 and got a hit in the form of this compound, AM80, also known as tamibarotene, which is a potent and selective retinoic acid receptor alpha agonist. In addition to AM80, in another library, they actually found a compound AM50, another very specific retinoic acid receptor alpha agonist. The difference between these two is that this amide is inverted. And when that is inverted, your EC50 goes from around 2 micromolar to around 400 nanomolar. That's in the mini GI assay. So right fast, I want to have a word about our assays over here. So up top, you've got the Presto Tango assay. The Tango assay is our preliminary screening assay. So when a project first gets up and running and the screening that led to these compounds, that's all going to be through the Tango assay. As you get deeper into a project, you'll get other assays online. And in this case, our predominant secondary screening assay is what's shown below, this mini GI construct assay that uses BRET1 signaling. You can already see from these two that the EC50s can be quite different between these two. I try to note which assay an EC50 is coming from. But if you get a jump, it might be because I'm going from, say, the Tango assay to the mini GI assay. So just something to keep an eye out for. Okay, so with our collaborators at UCSF, we decided to start with this AM580 structure, and Shuo Gu at UCSF did some analog by catalog, sent us some compounds. First round of compounds, the question that we were looking at is what happens with this left-hand side of the molecule here. And what we found out in round one is that if you don't have both ring systems, then all of these compounds are dead. So either with the phenyl ring alone or with the pyrimidine, no matter the position of the nitrogen, all of these compounds are dead. Okay, so what about a two-ring system? Well, another thing that we found out is that these gem dimethyls present on this hexane ring are crucial for activity. So you can see the three compounds in the left-hand column, they are all dead, whereas the three compounds in the right-hand column there were all hits with activity in the Tango assay. I just want to make a note right fast because these chlorines will come up in future structures, and while they lead to really increased activity at GPR 97, these gem dimethyls are required because these two compounds later on, when you put the gem dimethyls on, become very active, and they're not active here. Okay, so left-hand side of the molecules decided. Now let's look at the right-hand side. So with AM580, we've got this carboxylic acid para to the amide, and that's about 3 micromolar in the Tango assay. As you go down this column here, this methyl sulfonamide, you get down to about 1 micromolar in the Tango assay, and further below that is this tetrazole, where we're at about 700 nanomolar in the Tango assay. So that's very exciting, moving in the right direction. Okay, round two. So like I said, our starting molecule is a retinoic acid receptor alpha specific agonist. So we want to make sure that we are getting rid of that activity. The percentage values here is the percentage of activity, of your maximal activity of this molecule versus the reference agonist at retinoic acid receptor alpha. So for RAR alpha, that's 9-cis retinoic acid. So AM580 was at 55% of the reference agonist at RAR alpha. Now this tetrazole compound that I talked about on the last slide, unfortunately, is at 32% at RAR alpha. And beneath that, you can see that the presence of these chlorines ortho to the hydroxyl, while you've got decent activity in the mini GI assay, you're still at 27% in RAR alpha. Okay, so bad news. Let's come over here to the right for the good news. The good news is that this methyl sulfonamide up at the top, while not performing, which had reasonable activity in the Tango assay, not great in mini GI, but our RAR alpha liability is down to about 4%. So that's moving in the right direction. When you add this chlorine ortho to the parasulfonamide, you get better activity in the mini GI assay, getting below 1 micromolar, and your RAR alpha liability remains low at 2%. And down at the bottom, if you cyclize this methyl sulfonamide, you've got 0 activity at RAR alpha and sub-micromolar in the mini GI assay. So the sulfonamides, methylsulfonamides are looking very good moving forward. So off to round 3. Just over here, last look at tetrazole, tried putting a chloro ortho to the tetrazole ring. And while that had good impact in the mini-GI assay, it brought the liability at RAR alpha, made that even worse. So that's out. Below that, this 1,2,4-oxadiazolone ring is going wrong in both directions. So last call, these nitrogenous rings are out. But over here on the left, a good finding from this is that if you methylate this amide, you have, while maintaining the methylsulfonamide, you get your RAR alpha liability down to basically 0 and also greatly diminished activity at GPR 97, which is good from the context of having a negative probe. And this isn't too surprising that methylating this amide could greatly impact activity, given that we saw how important that amide was early on in AM80 versus AM580. Okay, so we've got a negative probe. Good start. So in rounds 4 and 5, we added 2 chlorines to this ortho to this methylsulfonamide, and that actually led to compound 289, which is our positive probe compound. Round 5, we actually wanted to see what happened if you replaced those chlorines with fluorines. And surprisingly, that greatly diminished the activity. But we counted that as a win because we can use that as a non-methylated negative probe. There's been some concern that just throwing a methyl group onto compounds can change basically the off-target activity, which is what oftentimes you're trying to sort of access with some of these negative probes. So having a more structurally similar non-methylated negative probe is exciting and makes for a more robust positive and negative probe set. Okay, so here's what the data looks like for the positive probe, the 2 negative probes, and versus the reference agonist of beclomethasone dipropionate. We've got about 140 nanomolar EC50 for our positive probe, and this is in the mini-GI Brett assay. And you can see from the graph that we've got better efficacy than beclomethasone dipropionate, and that both of our off-targets vary somewhat in efficacy, but the potency is sufficiently low. So we are excited about this set. All right, back to RAR alpha. And because these compounds were RAR alpha agonists specifically, we wanted to make sure that we weren't just diminishing the specificity for alpha, possibly gaining liabilities of beta and gamma. So we wanted to make sure to test all 3 compounds at all 3 retinoic acid receptor subtypes. And you can see from the table down below and from this graph we zoomed in here that there's functionally no liability with these compounds. That's for RAR alpha, but in the table, it's even lower than that for beta and gamma. So we're very excited to see that we really diminished that off-target activity. Okay, so we've got RAR taken care of. What about the rest of the GPCR? For compound 289, one caveat with this assay is that in the Tango assay, compound 289 has nonspecific interference in the Tango assay itself above 300 nanomolar. So you'll get a false negative signal above that concentration. So this assay is typically run at 10 micromolar. So obviously this is a lot lower than that, but it's what we needed to do for the compound. And at 300 nanomolar, the only hit that we got was GPR 97. So with those caveats, it's still exciting to see that we don't have any other off targets happening in the GPCR. For compound 815, our methylated negative probe, we did have hits at CB2 and melatonin 2. CB2 was not not particularly potent or efficacious. So that one's not really a concern. The melatonin 2 was a partial agonist and with decent potency. And so that's something that you would need to be aware of when utilizing this as a negative probe. Unfortunately, I don't have GPCRM data on 295 yet. There was a purity issue that has since been resolved, so that data is forthcoming. Okay. Schwo, our collaborator, had docked 289 in the structure. There is a solid structure, a cryo-EM structure of GPR97. So Schwo docked 289 in GPR97 and got two viable poses. One dominated by the methylsulfonamide interacting with this tyrosine 406 that's in the ECL2 portion of GPR97. The other positioning is with the methylsulfonamide down in the receptor interacting with this asparagine 510 that's on TM7. So he asked us if we could make mutants at these two sites and see if we could tease out pharmacologically which of these binding poses or which of these poses for 289 was the one driving the positioning. There's a whole host of work that we've done on that right now. I'm just going to show this one to start with. This is actually a glow sensor CAMP accumulation assay. Unfortunately, if you look through these, so we've got GPR97, which is a wild type. T250A actually modifies that autoproteolysis domain that I talked about earlier, making it so the blocking the proteolysis so that the N-terminal region remains connected. We didn't see any impacts from that with the activity in this assay. When the tyrosine was modified to an alanine, the beclomethasone dipropionate activity was greatly impacted. 289 was somewhat impacted when tyrosine was modified to a phenylalanine at this position. And then interestingly, when the asparagine 510 was modified to an alanine, all of these compounds suddenly became inverse agonists. It's not unheard of. This asparagine is known to be able to impact agonism versus inverse agonism, but it was an outcome we weren't really expecting. So right now, the standing is that with this N510 alanine mutation, our compounds are agonists in the mini-GI assay and the Tango assay. They're inverse agonists in the TruePath assay with G-alpha-13 and in the glow sensor assay, as I just showed you. And the N510A mutant does not work with the Brett human beta-arrestin assay, whereas all the other mutants do. And this still doesn't really let us know exactly what is driving the positioning for 289. So we decided to get a cryo-EM structure of GPR97 with compound 289, the positive probe. That is in process right now. And then once we have that in hand, we'll see what critical mutations are indicated by for the positioning 289 that are indicated by that structure, and then do more mutational work to assess those probe interactions. So that is where this project stands. I want to thank really everyone in the PDSP and the Roth lab. You know, there's 1,000 times every day that the people in your lab help you out, and it really sort of takes everyone to get these things done. So I want to thank everyone there in the PSP and the Roth lab. I want to thank our collaborators at UCSF, including Schwo Gu, Xiaobo Wan, and Bryan Roth, and our collaborators at Mount Sinai, Zhan Shen, and Dr. Umid Khanaskan. They helped out with some compounds for this, and most of the compounds came from enamine. So we appreciate their efforts. And obviously, I want to thank the IDG for hosting, and I want to thank all and for funding, and I want to thank all of you for being here today and for listening. And I will now open it up to any questions.